Good morning, good afternoon, good evening, everyone, depending on where you're joining us from. This is Mike Mazzarese with AST Environmental. And first off, thank you for joining us today. We have some folks still rolling in. So I'm going to go ahead and we're going to pause for just 1 minute and start the webinar shortly. Thank you. All right. Well, thank you. Thank you again for joining us today. If you just hopped in, this is Mike Mazzarese with AST Environmental, and this is our November webinar. And title of the webinar is Mackinawite structured iron sulfide for heavy metals remediation, abiotic versus biotic formation and case studies. Our presenter today is also from AST. It's Derek Pizarro. He's a senior product manager here at AST. And I'll let Derek introduce himself and provide his background on heavy metals. And Derek, I'll go ahead and turn it over to you.
Thanks, Mike. Is this good audio?
Yes, you're good.
Okay. Thank you, everyone, for joining us. Derek Pizarro, AST Environmental. As Mike said, I'm a senior product manager. And while I focus on several different aspects of contaminant remediation for AST, I've spent roughly the last 15 plus years with a significant focus on heavy metals remediation, both here at AST as a injection and mixing contractor, but also started on the product manufacturing side back in 2009. So what we're going to focus on here today is iron sulfide, specifically Mackinawite structured. We'll get into why that's important in a few slides, and then we'll talk about forming it either in situ or injecting an abiotic form, which is ready to go. And then we'll look at a couple case studies specifically for hexavalent chromium. And the second case study has hexavalent chromium, nickel, and antimony in it. So I first wanted to start with different reactants, reagents that we may have used as practitioners in the past. Today's focus is going to be on in situ injection. So this would be for both phreatic or vadose zone applications with the products we're talking about here, the Mackinawite structured iron. But typically, when it came to injectants targeted for heavy metals treatment, when we first jumped into this as injection contractors and practitioners, we borrowed very heavily from our history, doing in situ soil mixing, doing T&D, ISS, anything that was a more traditional, going back to the early days of CERCLA, where we transitioned away from hog and haul into more treatment and subtitle D disposal or on-site disposal. We borrowed heavily from a product standpoint of what we would look at to inject in situ. And so, a lot of those early products were lime-based. They were pozzolanic. They typically were very well suited for their applications in soil mixing and T&D, but not necessarily for specifically groundwater treatment or in situ injection, just from a practicality or equipment standpoint. So, things like secondary contaminants, like other heavy metals, chloride content, silica content, things like that, that wasn't really applicable, especially if you're injecting this in groundwater. So there was a period of time, even in the last couple of years, where we'd get comments like, well, that's not injectable, or that's not an applicable product to use in situ for this heavy metal or this groundwater regime. And that was absolutely true. So we had to look at coming up with different products. We had to work with different manufacturers. Myself, going back to my manufacturing days, we had to kind of reset the table and see what we could do if this product was going to be either left on site or injected in situ to treat groundwater for heavy metals. So the focus here is on a very specific type of iron sulfide, and I'm going to start with not all FES is the same, right? in talking with the manufacturer that we work with for a lot of these heavy metal sites, which is Redox Solutions out of Carmel, Indiana, um, we get asked a lot, oh, just FES, right? And we see this named even very commonly. I've got iron sulfide, right? But there's various forms of iron sulfide from the Mackinawite structure we're talking about here today. There's pyrite, there's greigite. Um, the last two are just non-reactive. They're not applicable for remedial applications. So when you talk with providers or you're looking at different chemistries out there, just obviously know that just because someone has an iron-based product or a sulfidated type of product, it may not be applicable based upon the parent material that they're either grinding or trying to create in situ. And that kind of leads me to this slide here about, talking about iron. So the contaminants we're talking about here today are heavy metals. A great example in terms of common use is hexavalent chromium site. Maybe some of you on this call have done this or are doing a site right now, but as practitioners, we've used everything from, ZVI to ferrous or ferric sulfate. Obviously, in this presentation, we're talking about iron sulfide, but there's a lot of different iron compounds that you could use to reduce hexavalent to trivalent chromium, right? So there's a lot of options and a wide range of costs associated with those different types of irons. There's also some other products which are not iron-based, such as calcium polysulfide, that may be applicable, but then there's pros and cons of that product too, just like with any product, right? Um, and then of each of these, whether they're iron-based or not, there's differences in efficiency, reactivity, persistence. A good example is calcium polysulfide injected into um, a groundwater setting with a high groundwater velocity. That's not going to be a great deployment for that product, right? You want something that's more granular, more of a slurry. And then there's other things to consider, right? With ZVI, we get passivation, so that may not be for your project the most applicable iron, not just based upon cost, but maybe something like a blended ferrous or ferric sulfate product might be more applicable, a buffered ferrous or ferric sulfate product. And then you have to look at costs, right? That's a big driver too. And the last part here, which we're going to touch on in the next few slides, is if you are going to use something that is iron sulfide based, where are you getting it from? How are you generating it if you're doing it in situ? So we're going to focus on both a biotic and an abiotic iron sulfide product here. So we're going to start with biotic, right? And the goal with creating iron sulfide in situ for the reduction and co-precipitation of heavy metals is a stable, highly reactive, again, it has to be Mackinawite structured iron sulfide. And the way you go about making this in situ is the first you have to look at your dissolved oxygen, right? You need to remove that from the system. You need to depress that and keep it low and maintain it, right? Without doing that, you're going to have issues with oxygen scavenging throughout this process. Once we've done that, we have to get biosulfidogenesis and oxidation of the ZVI, right? This is the process that's going to transform and create this iron morphology of iron and sulfide that's going to be reactive with the heavy metals that we're targeting in situ. And there's, different timelines for that to be created in situ. Obviously, this could be on the order of months to years in some cases. There's different ways to speed up those kinetics. But the variables, because we're doing this biologically, include different sizes, different iron morphologies, and then Fe mass. And that's not necessarily just total mass, but that's also agglomerated mass, right? What is the distribution of mass throughout the subsurface that you're creating in this biological process? And so if we juxtapose that with abiotic, right? Abiotic is made chemically in a batch plant. We call this synthesized iron sulfide. In doing it in a controlled environment, we have the ability to adjust molar ratios of the iron, the sulfur, even the aluminum, which is an important contributor to this overall product that we're making. It goes back to the structure and especially helps with these polysulfide interlayers that exist between the iron and sulfur within the product. We also don't have issues with creation of pyrite or greigite, right? They're both stable but non-reactive FES products. Those can be formed in situ if those biological processes to create the Mackinawite structured iron are not maintained, or maybe there's changes in phosphate or carbonate interference, right? Both of those can affect the ability for you to form biotic FES in situ. And then because we're doing this in a very controlled environment, the product itself is relatively to very uniform in size, depending on what we're making. we don't get agglomeration of the particles, or we don't get a biofilm through this process. And again, because we can adjust when we're synthesizing this product, you get multiple treatment mechanisms. You can target this for environments that maybe need a little more iron or a little more sulfur, depending on the in situ geochemical conditions, right? But once you go through that process and you identify the most appropriate type of iron sulfide, and then you can work on loadings through your bench testing. And that's really where you start to look at the different treatment and removal mechanisms you're dealing with, right? Especially if you have a mixed metal site, it may not be just as simple as using, a 2-to-1 molar ratio of iron to sulfur. It could be completely flipped around. It might be 1-to-2. And then through this process, because we have these polysulfide interlayers, we also have the ability to electrostatically charge a transformed, say, arsenic or chromium molecule. We have the ability to attenuate it into the lattice structure of the product itself. So that's our surface absorption. And then if you have a significantly impacted site, even say commingled with CVOCs or other VOCs, where we can take advantage of electron transfer, because of the structure of the product at any given moment, most of these formulations of a synthesized FES have up to 11 electrons that they can give and take from various ends of the particle itself, or of the molecule itself. So we have a lot of room to rebalance, so to speak, the transfer of electrons within this structure. So it's very flexible in a lot of heavy metal deployments. The next thing I want to show you, and I think this is one of the most important things from a reactivity, from a non-passivation standpoint, is you want to create very uniform iron sulfide. And whether you're doing this in situ or you're using something abiotic here, what I would like to show you here on these scanning electron microscope images is we have in A and B up top, we have in an upper row biologically generated FES, and on the bottom row we have synthesized or abiotic FES. And you can see that the particle size and distribution is vastly different between the two, right? If you look up top, it's a bit more amorphous. They seem to be sticky or agglomerated, especially in picture A. As we move into the bottom, it seems more homogeneous and uniform, right? The particle size is smaller. And this is important because it plays to immediate reactivity, but also long-term reactivity. It affects passivation. It affects availability to continue to either reduce or transform and co-precipitate the heavy metal or metals you're dealing with. So a more uniform product is certainly more aligned with what most of us would like to see from a reactivity point in situ, and that's longer-term treatment as well as immediate treatment. So as a practitioner, I like to not guess. I don't want to wait. And so on the left there, that's just a picture of the batch plant where they synthesize this in Indianapolis. Again, I would recommend if you're looking at a site, especially if you do have soil and groundwater samples, or just soil if you're doing this in the Vado zone, that you use either redox solutions, use AST, use a third-party provider, work with someone who's got heavy metals experience, who's got iron sulfide experience, do a bench scale treatability testing to make sure that you're looking at the right product or products. Or in a lot of cases these days, if you have a commingled site, organics and inorganics, that you work with the provider to come up with a specific formulation of the product itself, which again is possible in a batch plant. So we've mentioned a few things that make this type of product unique. Again, the synthesized product that we're injecting here is ferroblack. Probably one of the most important things to me I just mentioned on the previous slide, which was the bench scale testing and treatability. Again, because geology is so different site to site, things like pH, ORP, DO, not just the contaminants of concern you have, but maybe even some tertiary contaminants that are not targeted for you, or even just naturally occurring additional metals or geochemical conditions that we need to assess and design for. That may be part of the overall reason to do a bench scale treatability. And I know if you've worked with us at AST before, we do a lot of stoichiometric calculations and assessments based upon groundwater and soil data. We don't necessarily do a bench test. However, in the heavy metals realm here, I would absolutely recommend doing a bench test, because it is something that becomes very site-specific with these type of reactions that cause reduction, co-precipitation, right, convergency. Something like arsenic, right, different pHs, different ORPs is going to react very differently in situ than, say, something like a benzene or PCE would with some very minor swings in pH or even ORP or DO. So this is a slurry. Let's talk about injecting it in situ. For those of you who worked with AST, you know that slurry injection is kind of our bailiwick. We do this via high energy injections. So other ways to put slurries in the ground involve suspension agents, gasifiers, things that make a true particle suspendable, which this product, this ferroblack is, right? This is a true slurry. So this isn't something that's going to lend itself to traditional injection equipment and injection techniques. So we suspend it with high energy, and we do that because the addition of any component to that batch tank, regardless of how innocuous it is, regardless if it's food grade, etc., is going to have some effect on one of the parameters that we would like to succinctly control once the product is installed, right? It could be something as simple as the guar breaking down and having immediate to short-term reaction, right? Or it could be that if you add a viscosifier, it may not distribute as well as you would like, depending on the injection equipment you're using, right? It goes in, it suspends well, but maybe you're not getting the distribution laterally or vertically that you're looking for. Again, because there is some variability in using a synthesized iron sulfide here, there is a little bit of heterogeneity in the type of particle sizing and solids we're dealing with here. But typically, most of these formulations end up being somewhere between 8 and 11 pounds per gallon. So it's a very true slurry that has to be injected. So it does take very specific injection equipment. And so the way that we do that is either going to be radial co-mixing in coarse formations, or we're going to be doing fracturing in more fine-grained formations. And whether that's fine or coarse, we're doing overlapping top-down injections. There we go. All right, so here's just a quick schematic of those top-down injections. Apologies for the drawing by a geologist sketching this out. But basically what we're looking at here is, and don't think of these as 2D features in the subsurface. There is dimensions to this on the order of millimeters, or excuse me, of centimeters up to inches in some cases. But certainly as you move into coarser formations, these swaths end up being on the order of 8 to even greater than 12 inches in verticality. So these are true interleaving mixtures as we go through each injection point. And you can see there we offset each injection point to create that feature in the subsurface. So this is complete treatment, right? Whether this is injected in the phreatic or vadose zone, this is going to be just as good as doing in situ mixing, especially at depth where you're limited and have to move out of a zone that you could use yellow iron to do these installs. And so with that, not just the equipment matters, but what you're putting downhole matters. Again, doing slurry injection, we create our own injection tips, and these will be predicated upon the slurry we're dealing with, in this case, the iron sulfide. But then we look at the geology and depth that we're injecting at. And there's a few other things that we would tweak based upon our tip selection and our injection pressures and velocities. But generally speaking, it's not just you can't just show up and use an off-the-shelf tip. You can't just use off-the-shelf pumps. This is all a very specific and intentional system that's being brought to bear on your site to install these iron sulfide slurries. And just to give you an example, when we're in shallower overburden settings, right, we may be trying to inject at a lower flow rate. When we move into deeper overburden settings or we move into transition zone like weathered rock, saprolite, and very much so when we move into weathered bedrock, we're talking about changing our flow rates and pressures to get distribution of this material. So this is just an example of one of our pumps called a triplex hooked up to an overburden injection tip and chained to a sawhorse here. And we're just showing you at different flow rates what this distribution is giving you and why we're doing it. And you can see that the intent here is to be both specific with loadings in the subsurface, but also create that vertical and lateral interlapping, interleaving and overlapping in the subsurface. And so just to hammer that home, here's just an example of two cores. Right on the left, we have a fine grain material. That product there, you can see that it's black, just like the ferroblack, even though in that core that's not ferroblack there. I'll show you a picture of a ferroblack core coming up in one of the case studies. And then on the right, we're talking about the radial co-mixing or fluidization of the formation, which gives us that complete intimate mixing of the product, the slurry, and the formation itself. And then, so where do you use a heavy metals treatment product in situ? Well, especially if it's groundwater, you're talking about doing source zone injection in a grid pattern. Again, that's how we create that complete networking of the product in the subsurface to get treatment. But probably one of the most common deployments that we are looking at to, we're working with or have done to date is some sort of reactive barrier or zone. Obviously, many of you on this webinar here today are familiar with the upper left there. Installing a permeable reactive barrier to bisect the plume. Same thing applies for heavy metals. We've also done some modified deployments there. This is a more of an ex situ setting there. We've preconditioned the ground there with a magnesium oxide, and we're creating a modified PRB that will be covered up, and that's a discharge point for treatment water. So that's an infiltration basin. And then the more traditional direct soil mixing there you see on the bottom right. So again, while we focused on injection today, there are other means and methods for us at AST or you as practitioners to install this product in situ. And probably the most important thing is, regardless of your method of installation, this Venn diagram is really the holy grail here of creating good treatment in situ. But obviously, with heavy metals, this is just as important, right? And the last piece there, the longevity, is something that the reason we like them at ASTs, the iron sulfides give us that longevity we need, which is really important if you are doing a PRB or PRTZ. And so from an experience standpoint here, both myself, other PMs at AST, all the states, colored or in black, we've had either ISS or T&D metals design and testing experience. And then in more recent years, both us and Ferroblack have worked to inject the material we'll talk about here today. Those are the states in red. And then we also have some scheduled projects coming up. We've highlighted those in blue. So we've used these in a lot of different geologic settings for a lot of different clients. I will say, as a practitioner, we're starting to see the injection side of this product ramp up significantly. When these products first hit the market well, we're going on a while now. It's probably about 10 years now, in terms of serious deployment. We're starting to see definitely a focus on injecting these, not just because we're finding more flexibility and reasons to do it from an injection standpoint, but it's looking at sites that are not as easy to do, right? A lot of the heavy metal sites historically have been yellow iron, soil mixing type of sites. Now we're starting to find that we can do this on more challenging sites through injection. So if anybody on this call, on this webinar, has a site in Hawaii for heavy metals, Mike's based there in Denver, but I'm going to leapfrog him and take that one off his hands. So you just let us know after this webinar is over. So let's focus on a case studies here before we can take some questions. This first one here is a hexavalent chromium case study in the Northeast. Through a treatability study, we'll talk about in a second, ferroblack H was selected. Again, this is a synthesized abiotic Mackinawite structured iron sulfide. And what we're looking at here by weight is a product that typically is manufactured about 1 to 2% by weight of soluble sulfides. And then there's an insoluble sulfide component of that. And the reason we have both soluble and mostly insoluble is to give us both that immediate and long-term treatment. Again, the product itself, because of the amount of electrons it has to share, right? We have a lot of flexibility and a lot of changes that are happening to the product in situ when we're treating and reducing a heavy metal in this setting here. And for a contaminant like hexavalent chromium, that gives us a lot of treatment capacity to get to that trivalent conversion and precipitation in situ. Again, I mentioned different types of slurries here. This one was installed at about 10.1 pounds per gallon. And from our standpoint, to prove proof of concept in situ, it was really easy to monitor this. And we'll talk about some of those, but really easy to monitor through some in situ parameters collected via groundwater to know where we'd put the product. And so the consultant on this product did an RDC. This involved a remedial design characterization of soil and groundwater samples. They were sent off to Redox Solutions in Carmel, Indiana for subsectioning and dosing and subsequent evaluation, generating some laboratory data. And we were tasked with looking at a 30-year lifespan for 5 injection transects. Again, these were not true PRBs until we got to the boundary line of the property. We were looking to create reductions throughout a large swath of this plume in situ. And so because of the size of the plume, because of the lifespan we were trying to affect, we had a significant mass of reactant required. They looked at ZVI, they looked at some other iron sulfides, they looked at calcium polysulfide. Uh, those were either extremely expensive in comparison to the ferroblack, or the persistence and longevity just wasn't there. And so in the end, looking at very specific samples from each transect where this would be installed, each transect got a very specific dosage of that ferroblack H. Now, this project here, we actually did not change the product transect to transect to transect, but there have been projects where it makes sense to use a different formulation in different areas or different PRBs to affect the treatment you're looking for. Here, that wasn't necessary. We just changed the loadings by transect. We did have one other challenge at this site. We did have to install this into a heterogeneous glacial till and also a fairly hard sand unit that overlaid it. And so we elected to do this with rotosonic drilling. So we used a process here we call geotap, which I won't get into too much in this presentation here, but there are materials on our website and YouTube that talk about it. But basically, this is a pre-drill access to the subsurface, right? We're creating a pathway for us to do DPT injection in a geological regime that would normally result in DPT refusal. So we pre-drilled each of our injection points here. In doing that, we had to start the sonic drilling well ahead of the injections because the injections happen so quickly, which we'll talk about in a second, that we would have caught up to our drilling crew if we had not done that. Here's just an example of one of the sonic rigs we're using on that site. We had up to 2 at any given point, but typically we were running 1 full-time and 1 assisting. This is not a sampling program, but what we did here is we tracked using the sonic cores, the geological unit itself, because there were thickening and thinnings of the targeted unit, and also variation by depth as we moved across each transect. So in taking these cores, we would know which was our top of starting depth and our termination depth as we moved across that transect with injections. You can actually see in the background, this picture here, the ferroblack being delivered in IBC totes. And so when it came time to injections, we did use our typical AST setup. We used 2 1/4 or 1.5 inch injection rods, depending on the depth. We looked at the injection point spacing that was predicated upon depth, geology, and product loadings. So those all affected how far apart each of those injection points were. And because of the depth and because of the loadings we had to install at the site, we elected to use our triplex injection system. Some of you that have worked with us before know that as our bedrock system. The best way to think of that is it's an extremely large pump that runs off the PTO of our Kenworth truck, and we can pump up to 280 GPM and even upwards of 2000 PSI if we need it. However, I preface that with we're trying to control these injections and affect distribution. We're not trying to use it as a sledgehammer or create propagation outside of the area that we're not targeting. So again, a lot of our initial startup was that optimization and leaning on prior injections and methodologies that we had used at this site and others before to create that distribution. A couple other pictures there of the process: injection truck and support trailer on the left, DPT on the right. Just a little more about the triplex pump. We don't always use this. A lot of the ferroblack installs that we've done, we have used our dual pump tow behind trailers, which many of you have probably seen for treatment of CVOCs, petroleum hydrocarbons, other sites. But here again, we did elect to use that larger pump. So lessons learned slide. This was the largest ferroblack install that we've done to date, that'll change next year. But one of the things that was interesting is because each transect was unique in both loadings of product, depth, the geology itself was fairly consistent, though it did undulate with depth and pinch and thin. We spent the first couple days working on shot volume and flow rates to affect distribution in the subsurface. And we were confirming that distribution in the subsurface by using temporary wells, implants, piezometers to monitor distribution via changes in geochemical conditions. The ferroblack itself also has a colorimetric change. The product is black to very dark gray in nature. So if you pull a groundwater sample, it's very evident to see if the product's been there. And when you put that in your dip cup, you're going to see a significant change in pH and ORP. So it was very easy to monitor influence of injection through those implants. And once we got that dialed in, we were able to continue to use those notes to optimize our distribution at this site. Other things we had to deal with, preferential pathways. This was a site in a old portion of a large city that had been around for a long time. The site had gone through several iterations of buildings and rebuilding. The building at this time was raised, but they had infilled a canal years ago. There were some former sheet piles, some old wells, some old investigatory abandonments. Basically anything that would be a potential conduit for daylighting or create issues with short circuiting was definitely available to us at this site. And one of the reasons I can add sheet pile to this lessons learned is we definitely found one of the transects. We found the old sheet pile after they yanked it because we had this nice, beautiful daylighting event occur, which we had to offset and deal with. Again, that unfortunately wasn't noted on the construction maps at the time. Had it been, we would have moved a little bit further to the south from that former sheet piling. Again, that's just a function of the energy of injection, being able to find those former um, installations and preferential pathways. So please let's all abandon our wells and and core holes as best we can, just because we never know what we're going to do in the future. So last summary slide here for this installation, almost 35,000 gallons of ferroblack, 5 transects. Injection took a little less than 4 weeks. We did almost catch up to our pre-drill installation that I talked about earlier. I mentioned a few of the ways that we assessed distribution there on the left. We also, through that optimization, found that most of the transects that we did in the upper and lower injection intervals, we call them shallow and deep, we did a slightly different pressure and shot volume setup to the point where in the shallower zones there, which were typically about 40 to 55 or 60 feet BGS, we actually did a sequential shot of 200 or 100 gallons as opposed to one 300-gallon shot at the lower interval. And again, through both the temporary monitoring points and also permanent monitoring well installations, groundwater monitoring at the site continues. We are converting Hex to trivalent chromium, and the product itself, from a pH, ORP, and geochemical parameter standpoint, continues to be persistent as expected. And I'll wrap up here with just a quick look. This is more of a visualization where we have a little bit more data because this site's been in the ground longer than the last one. But this is a mixed metals case study from the Midwest. These cores here are actually post-injection. You can see in the 2 middle cores from 8 to 12, 12 to 16, and then a portion of the 16 to 20-foot core that the ferroblack was well distributed in the subsurface. Again, it's a very evident change here, right? Like most of this material is kind of a tan to gray sand, trending down towards a glacial till unit, which tends to be coarser and a little bit darker. You can kind of see the beginnings of that in the uppermost core. But again, this is just a real easy visual, even in post-conformation boring, which we've been able to repeat at several sites. It's very easy to see in the subsurface if you've gotten distribution. And so at this site, we'll talk about a few here. Here's nickel, right? So post-injection on the left in the next few slides, or excuse me, pre-injection on the left for the next few slides, post-injection on the right. Here we are looking at the change in nickel concentrations after 3 months. Here's our hexavalent chromium. This is 15 months in situ. And then here's antimony after 3 months. So again, you saw some of the different time frames we're dealing with depending on the concentration and the metal itself. Those conversions have different lag periods associated with them. But generally, because this is an abiotic treatment mechanism, most of your sites you're going to be seeing those conversions on that 3 month to upwards of 12 to 18 month time frame. There are some other things that can affect that. Obviously, if you have a mixed organic, inorganic contaminant site, that could that could change the time frame to reach the goals you're dealing with. Again, we're going to set those expectations up front in the bench scale treatability process. And I'll wrap up there. I appreciate your time here today, and bring Mike back in.
Thank you, Derek. So we'll open it up for questions. Please use the Q&A and not the chat at the bottom of your screen. I guess Derek, if you don't, I can go ahead and kick us off. So you mentioned bench testing before. I guess, is that recommended for pretty much every site? And maybe you could explain a little bit what's all involved with the bench testing.
Sure. I would personally recommend it for every site. The the inorganics, the treatment of inorganics here, specifically the heavy metals we've mentioned, which are usually the ones that hit our desk are hexavalent chromium, arsenic, lead. Like those are probably the three most common ones. But you start getting into, nickel, mercury, selenium, molybdenum. You're talking about products, or excuse me, you're talking about contaminants that are very unusual in some cases, whether they're, in situ groundwater, whether in situ soil. They are not something many practitioners deal with, and they, especially in the case of a metal like arsenic, which can also be an organometal, there could there's a lot of parameters geochemically and co-contaminants that could affect their treatment. So I would say probably more so, at least in my opinion, probably more so than any other organic contaminant. Heavy metals treatment certainly requires a bench scale study for each site, and that would include both, soil and groundwater if it's a saturated zone. If it's not, definitely soil and multiple samples, right? You're going to see with metals like you do with some organic contaminants, very heterogeneous and very stark changes in horizons as you move, right? Like they may be very attenuated in a horizontal layer. Some are more mobile. They tend to spread and distribute themselves further. So, it can't just be like one or two soil samples. It's got to be either several samples from very specific locations that have been identified, or a composite sample, or several groundwater samples distributed throughout the area. And the benefit with that is, from a treatability standpoint, is you can also make those optimizations by area as well, right? Like in that transect example, we didn't have to use the same loading on transect 3 that we did at 1. Like 1 was the most impacted, so that got the heaviest loadings. Probably the last thing I would note, other than deriving the product or products and the loading rate or rates that you need through that bench study, I would make an overarching comment. Whether this is mixing or injection, you also need to set a bare minimum weight loading percentage in the subsurface. Now, from a yellow iron, like an ISS, T&D standpoint, we usually as practitioners set that at about 2% by weight. Anything less than 2% by weight, it's going to be very difficult to um, homogenize that unit. Now, in situ with injection, especially with the ferroblack product, because it's on the finer side of the slurry, we can get very good distribution and contact. So we don't necessarily have to constrain ourselves with a 2% loading rate. We might be able to back that down and say maybe even a 1.5 to 1%. Again, depending on the geologic regime and our goals, and if it was source versus PRB settings. But a long-winded answer there, I apologize, but there's a lot of variables that, for every site, for every metal you're dealing with, that do require you to do a bench scale study up front.
No, thank you. There are actually a couple questions have come in that we can sort of tack on to that. So one was bench test length, number of reactors and matrices. So you've answered a couple of those. Maybe you can maybe for how long the tests are run and maybe the number of reactors, which you sort of touched base on that a little bit already.
Sure. I would say that that's a very site-specific question. Where I would say you get into the multiple samples and aliquots and reaction or reactor studies that you need to do, those are probably more aligned with a mixed organic inorganic site.
Hmm.
Certainly, you're going to want to look at those on the order of months. I do know that there's a site being tested right now in the Redox Solutions lab where they've got samples running out past 12 months now. And
Hmm.
the reason there is they are seeing immediate conversion or very near term conversion of the hexavalent chromium they're dealing with, but they've also got some PC and TC in the mix. And the blend that they've derived for that site there, that's where you need to carry out some of that longer term monitoring to not just affirm you're getting that dual treatment, but also that there's no tertiary effects on um, maybe not so much the hexavalent chromium, which when that conversion takes place with this product, right, that's a very stable metal and it has a very, very, very high standard um, in groundwater. So you're probably looking at more about maintaining or not mobilizing tertiary or naturally occurring metals in that setting, which in our experience we have not seen with this product. That's one of the reasons we like it. But again, stepping out that time frame is very useful if you have the time to do so. Again, that will be a very protracted bench scale though. Most of these sites, you're looking at a couple weeks to kind of do an if-then scenario, right? I dose it at this 2, 3, 4%. I get this result.
Hmm. Hmm.
Do I need to move on to the next sample? Do I need to check the other samples? Can I eliminate a dosing? Things like that.
Okay. This one is a little more site specific, but it actually that one doesn't cover bench testing, so we'll actually come back up here to the top. Are the ferro-black reactions reversible, or do change in site conditions produce any remobilization?
Metal specific, but generally the conversion, change in valency and co-precipitation and attenuation to the product, or in some cases you could use the soil or another product in the blend itself. I do know that you can create some attenuation onto a subset of minerals, or even if there's a activated carbon or biochar in the mix, you could create a very permanent setting there. The one
Hmm.
thing about these products, if you are injecting these in a source zone, is the persistence of the pH and ORP changes, which those two parameters are going to affect and dictate the performance of most of your heavy metals in both near and long term. There are some other parameters that play into that, like DO, but those are generally the two that dictate how effective this is. And so we don't see, at least we haven't seen, um, any reversion, right? I'm thinking of arsenic sites, um, specifically. We haven't seen that as an issue using this product. Now, I
Hmm.
would say, well, that's a rabbit hole I don't have time to go down. I'll leave it there. Sorry.
Okay. Yeah, what you kind of touch base. One of the other questions was, related to pH. I think you just answered that. How is performance affected by groundwater pH? Is there an optimal pH range when applying this as a treatment option?
So, quick response there. Um, the product itself can overcome a lot of sites where the pH may be on the lower end of neutral to even acidic. So we will do some natural buffering there. But again, because if you're using a synthesized product here that we can make alterations to the product itself, we're also afforded the ability to change some of those other geochemical parameters to account for a low pH, or say we already have a naturally existing high pH. We
Hmm.
could work with that to come up with the correct product to fix that situation, or at
Hmm.
least optimize it for the treatment process.
Okay. Let's see here. We'll come back to this one. Any experience with calcium polysulfide and how it compares?
Yes, experience. Used both. I would say my personal preference these days is for the ferrous, or excuse me, for the to use the ferro black versus the calcium polysulfide.
Mm,
The calcium polysulfide being a solution is going to distribute very easily through several injection methods, but from a treatment capacity standpoint and a residency standpoint, it's a bit from a treatment standpoint, it's significantly lower than the Mackinawite structured iron. From a residency standpoint, it's just like any other um, solution you inject, right? Depending on your groundwater velocity, that's going to dictate your residency time. And so for me, if I'm doing, which is the majority of the projects I work on, that you work on, Mike, like we're doing source zone treatment, we're doing PRB or PRTZ installs. I like a product that I put it where I know I need it and I know it's going to be there after I stop injecting it. It's not going to migrate with groundwater. So um, there's nothing, specifically wrong with some of those other products out there, but from a cost optimization, from a treatment efficiency optimization, and a persistence standpoint, I find that we're being asked to use or we're recommending iron sulfide a lot more than the other products these days.
mm. Okay. Let's see here. In nature, Mackinawite can contain trace nickel. Does that present complications when applying the product to sites contaminated with nickel? And can it be controlled with certainty when synthesizing abiotic FES?
So that's probably a question better for the manufacturer. I know we've looked at um, tertiary inclusions of metals or tertiary co-contaminants with several products. Um, Up front, I mean, nickel's not typically terribly a hard constituent to treat, and certainly if if it's in the product, you don't want to put that in situ if you don't need to. But um, I know we've had to do assays and answer that question for clients before. I just don't remember off the top of my head um, what they did aside from that assay. So if you reach out to me, I can find that for you after this webinar and give you a better answer.
Yeah, I can send you the contact. That'll be in the Q&A log. So we can go ahead and circle back with you on that one. Let's see here. Do you recommend passive flux meter studies to measure Darcy and flux as part of the treatability study process?
Sure. I'm not, I mean, if I'm doing a PRB, I certainly need to know a lot of groundwater parameters, right? So if you want to use a passive flux meter, if you want to use other means and methods to evaluate groundwater conductivity and mass flux, I'm all for it. That's, I mean, I don't know, Mike, I know you've probably got more experience with PFM than I do, but
I
um,
do from a VOC standpoint because I mean they obviously have the activated carbon piece to them, so they're going to absorb the VOCs. I'm not sure if there is a version. I'm not sure if
yeah.
there's a version that's specific to heavy metals, but if there is, I mean, if nothing else, and you're just getting the tracer data to be able to dial in your depth discrete um, conductivities and velocities, then that's going to help in the ultimate design of any PRB,
Yeah, I mean, I wouldn't use them to, I mean, the activated carbon is not the best way to capture and evaluate that, but
right?
if you're using those to evaluate the groundwater um, parameters themselves from a velocity standpoint, then yeah, I don't have a problem with that. I'm a more simplistic guy. I typically lean on the slug testing, but you gotta adapt and evolve. I know a lot of people are asking that question these days for some of the organic sites we're working with.
Mm. Okay. All right. Let's see here. With the bench testing caveat, what post-treatment concentrations of arsenic could you achieve if you're starting at 50 ppm, 50 milligrams per liter?
Uh, that's going to be really difficult to answer without doing a bench scale test to evaluate all the, effects of the groundwater and soil that are, affecting the attenuation of that arsenic. But has it been done? Yes. Has it been done for a site injected in situ? Yes. But again, that's going to be very site specific. I would say probably just roughly you're talking on the order of needing to install somewhere from 4 to maybe 6% by weight in the subsurface. So
Mhm.
that's probably, well, again, it's going to be depth and geology dependent, but that could be even two separate injection events to
Yeah,
convert that much
or
arsenic.
a or a or a mixing application, right?
Yes, if it's doable. Yeah, that, I mean, that's the overarching comment too. If you can do this mixing, right, especially if this is Beto, you
Hmm.
should do it. Obviously, if you're attending this webinar, you're probably dealing with more sites that are at least for injection. But yeah, if you can soil mix it, you should do it. I mean,
Hmm.
that's expeditious in most cases, and it takes variables like short circuiting and daylighting off the table.
Hmm. Okay. Can you speak on the second case study, what injection approach was done, and any other remedial technologies applied to the site, such as like a source area excavation?
At that site, yes, there was historical uh, site removal. There was historical T&D. They did use, well, at the initial outset, some of that was not the Ferroback product, but on subsequent work at that site, it was mixed, treated, and disposed in a subtitle D landfill. From the injection standpoint, you're talking about something that's a fine to medium, mostly fine to medium sand with some silt and a little clay up front at the upper layers. As you moved closer to the till layer, there was a coarsening of the geology. So there, that injection, you're talking more of a radial co-mixing or flooding of the formation to create that contact. That was not a fracturing site, so to speak, or at least a traditional fracturing site like you would see with a clay, a saprolite, a weathered bedrock.
Okay, thank you. We got a couple more here. Do you try to determine the minimum demand similar to soil oxidant demand for ISCO to confirm whatever is present in soil and groundwater that can be reduced and therefore is a demand on the reagent besides the target contaminants? Or do you simply use your 2% rule of thumb?
So the 2% rule of thumb was for soil mixing. Um, that's just to create contact. You know, even if you're bucket mixing, if you're doing rotary head, you know, a good operator can do a really good job of thorough mixing, but still there are some variabilities, especially if you have a more cohesive soil. So again, that's just kind of a practitioner, you know, minimum dosage. When it comes to injection, getting below that, say in the 1 to 2% range, which is more stoichiometric than it is about contact and the operator's ability to create contact. Um, I personally wouldn't call it similar to soil oxidant demand, but you are talking about going into the lab and evaluating the dosage rates. And the one thing I would say is with metals, at least or especially at the outset, but even as these bench scale studies progress, is don't overthink them, right? Always start with some very simple kind of thumbs up, thumbs down, because these tests are not terribly expensive, right? You're not talking about weeks and months uh, with a metal site like you might be for some of these columnar reactor studies with an organic site. It could be something as simple as, okay, at the outset, I only have the ability to take one composite sample of soil, send it off for testing, or I've only got the ability to take so many groundwater samples and have the lab put a dosage array onto it, right? Like if you know enough about the site through groundwater or other sampling events, you could say, all right, we should do 2, 3, 4 here, or we don't know a lot. We should do 2, 4, 6% by weight, right? Yes, you're going to burn a sample, but they're not that expensive, and it's going to give you some very high level data to start to drill down into. So, um, don't start, for me, don't start with complex, very in-depth, lengthy bench scale studies for heavy metals. You may get there, but you can learn a lot by only spending, a couple $1,000 over the course of a few weeks to get into a dosage array. And if you need to drill down into it, especially if it's a groundwater deployment, you can do that. But um, I always like having a juncture, right, where I can make a decision. All right, I did this very simple test and I'm here, and that's told me this, and I should, kind of like choose your own adventure. Where do I go from here now?
Mm.
let the data kind of take you in that direction.
Okay. We're down to two more. So, and this kind of touched base on this a couple times, but question is, do you raise the pH after ferro black injection to drop the precipitation reactions? If so, is there a waiting period and how high the pH is elevated?
The effect of the product is essentially instantaneous. Like it's very drastic. So when we were doing the example of the hexavalent chromium site, once we finished the injections abutting one of our piezometers, straddling a temporary well, we could go in and take a grab sample. And if the groundwater was already changed, right, the colorimetry was different. We saw the pH and ORP changes. So once it's in contact with the area, these conversions are happening very quickly. And then from a persistence standpoint, again, because we have a slurry product, we have a mixture of soluble and partially soluble sulfides. We have that continued treatment and maintenance of those parameters that we're looking for. So I think it would be very easy with some piezometers, some implants, some temporary wells to immediately monitor, and then subsequently over a period of time, depending on your say well permitting, depending on what you're using, you can continue to monitor those parameters very easily through grab samples.
All right. Well, sorry, excuse me. We're down to one more. So this one's more on the injection side. Have you had issues pushing contaminants off site due to high energy injections?
So in terms of moving any contaminant around doing in situ injection, probably the first thing to do is lay out your injection grid before you get to the site on your map and come up with a way to work your way into the room, right? You want to start on the edge and then start leapfrogging, hopscotching your way throughout that injection grid. Nobody wants to push stuff off site, right? So that's a consideration if you are towards a boundary line or a sensitive receptor or some other feature that you have that consideration. It's really more about sequencing and selecting your injection locations at the outset than anything else.
Yeah, and I guess just to add on to that, if there are sensitive features, we have in the past and used a tighter grid spacing in those areas because with the tighter grid spacing, you get lower volumes. And so it's easier to keep the reagent within your design ROI. And also, I guess one thing to keep in mind is that what we've talked about today are primarily slurries. And so the percent pore volume that you're injecting is going to be much lower than other, say, something like CPS, right? Where you're going with more low pressure, low flow, high volume injection, slurries. So we tend not to see that. And like Derek said, we kind of work outside in, kind of work toward the source area or in place sort of a PRB, say on the down gradient side where the concentrations are not as great, and then work yourself back to the source area. Um, that's another, I guess, kind of good practice methodology that we use on all of our injection sites. So, anything you want to add to that, Derek?
No, no, that was great. I appreciate your addition.
Okay, well, we're almost up against it. We're at 1 minute before the hour. So great, perfect. Thank you, Derek. We're right on time. Get you guys back to work. If anyone has any questions, you can reach out to myself or Derek directly. We'll go ahead and follow up with an email. Um, you'll probably see that from me, and it'll have Derek's contact information as well. This is also being recorded, and it'll be placed onto our website within the next few days. And so if you want to share that with a colleague, please feel free to do so. And we hope you enjoy the rest of your days and the rest of your day. And Derek, thank you very much.
Thank you, everyone. Thank you for your time.
All right, take care.